to look at Network Plus, the certification Network Plus. Lots of resources. One of the other things that you have is, and I think that you get the Professor Messer video series that they give you links to. You can get the Network Plus and Security Plus. I think both of them are still free, so those are available to you anyway. But the first thing is the objectives of the course, and it is correctly use fundamental network terminology. One of the things, and a lot of former military here, a lot of the things that we do revolves around the language that we use. If you're in the Navy, they got their own language. The Seabees, I'm sure they have their own language. The Army has their own language. And when we use that, it doesn't make a lot of sense to everybody else. Same thing happens with networks. We use this language, and when we do something else, it may not make a lot of sense to other people, but we have those things. And then identify physical network technologies, including common components, their functions, cables, connectors, and Ethernet standards, and we'll look at those things. Physical network technologies, the topologies really follow into here. Physical, we're going to have two types of topologies, physical and logical. Physical is what it looks like, and logical is the way the electrons flow. Try to make that. Read IP addresses. Explain common TCP/IP protocols, and the common TCP/IP protocols. TCP, and when we get to there, TCP and IP kind of go together. Actually, TCP and IP generally go together. UDP and IP could go together. Two protocols, number of protocols that are available there, and then use TCP/IP troubleshooting utilities. One of the things that I like to do is to, and one of those folders you saw in there is scans, and the scans are Wireshark. If you want to look at those things, you can download Wireshark for free and install it and open those scans. What I like to do is look at the data so that when we talk about this stuff, the theoretical, okay, let's look and see what this actually means when we go using a protocol analyzer, lots of terms, protocol analyzer, sniffer, to see what this stuff actually looks like when it's on the network. Recognize the differences between switches, routers, including the functions on the network, common features, and control protocols, and we'll talk about those. And you probably already got a good idea about that anyway already, because I expect that everybody at home is using a router, using a home router, and then that home router is a 4-port switch which you can plug into. So you can either get out to the internet, or you can work internally within your own network inside your house, and figure your whatever that we go from one to the other. I was going to say your TV, but we configure them from them. Identify technologies used for consumer internet connections as well as global WAN infrastructure. And the consumer protocols are relatively new. This is the Internet of Things, the smart house, the Nest thermostats, the control with the Google Nest or whatever you're using. I don't have a smart house, but we have protocols to do that. And I keep using the word protocols. Protocols is simply a language. We're using English. If we were in Germany, we'd be using German. That would be our protocol. In networking, the Internet of Things uses a language called Zigbee. When we're going to do this course, when you log into this course, we use a protocol called HTTP, and in this case UDP, although we keep saying TCP to do those things. Explain the principles common to wireless networks as well as specific features and standards used by the 802.11 Wi-Fi Internet of Things technologies. Recognize the principles of cybersecurity, common threats, security controls, transport encryption protocols. So Security Plus kind of gets introduced here too, and that's not atypical of any of these things. Although I think that, well, I was going to say A+ is kind of the most standalone, but then you put the NIC in and you connect the NIC to the network, and so you get a little bit of networking in there too, and maybe put an antivirus software on there so it touches in the security. So all of these have a little bit of overlap. Secure the network by placing network security components using central authentication systems and hardening your network on multiple levels. And that central authentication may have been some of the issues to get onto these things tonight. to get to the course itself. Describe the evolving use of networks such as of IP networks for voice, industrial, and storage technologies, or network-based virtualization and cloud stations. And I'll use a virtual server a couple of times for some demos. I also like to do demos. I use Packet Tracer, which is available in that download. If you really want Packet Tracer, just search for free Packet Tracer from Cisco, sign up for the free course, and get the whole thing. Because if you just get it and install it, you have to use the guest account, which doesn't have all of the capabilities of it. If you get the free account from Cisco, you get the full. Monitor and optimize traffic on diverse high-performance networks, including fault tolerance, disaster recovery, and incident response procedures. Plan, install, maintain, and upgrade a network using a consistent methodology and secure organizational policy. So that is the kind of the broad overview of what the course is about. Chapter 1 is fundamentals, and this is where, if I insult some of you who've been doing this for a while, I apologize, but we got to start with the basics of the whole thing, and then we'll hopefully work our way up to some mystery, solving the mysteries that we were talking about, because it is sometimes it's a puzzle, sometimes it's a lot of different things. Let me try to save the attendance here. It's credit. You'll get credit anyway. The chapter 1, the fundamentals, about basic network concepts, terminology, how networks are classified, about the OSI, TCP, IP models, network models. That's the one that when we do it, I expect when we get done, if you guys were chatting with each other, you say, I don't understand any of this. What we're going to do is have a bunch of theory here. And as we go through the course, we're going to try to make some sense out of that theory. But it is a model of how data flows from point A to point B, gets from one location to the other, so that you can get to Leader Quest, so that you can get to Zoom to do these things, and then how to apply the troubleshooting methodology. I'm going to try to, and I have one of the other things is, before we get into Module A, which is actually relatively short, what has worked for me in the past, there are 11 chapters here, which means that one night, and it's day 5, Friday, a couple of short chapters, we'll get 5 and 6 done. So basically what we're going to do is one chapter a night. Tonight with the lab, maybe you may say, oh, this is a little short, I got shortchanged tonight. Hopefully you didn't get shortchanged tonight, but we will, and hopefully you'll get shortchanged in the course. But what we'll do is try to do one per night as we go through. And also I'm going to try to, and I have been fairly successful, having an hour at the end of the class for lab time. You have if you don't have it yet, you'll get in your email the link to the labs. Please do the labs. I told you I've got a bunch of certifications. I've probably taken, I don't know, I got them at one time, 45, 48, 50 cert tests. And I can tell you from experience that it is a whole lot easier to answer questions about something that you've done than something that you read in the. Please do the labs. And all you VA guys, you got to be there anyway, so you might as well work on them while you're there when we get to that. And tonight we'll have a little short ones. And again, it may be a little bit of a short night, but not much. Module A of this one, and there are the 4 modules in here: networking concepts, network connectivity, network components, and then the goals and challenges of network design. So when we look at connectivity, and you guys do connectivity, you do networking, I'm sure, all the time, and you may or may not do a Facebook or those things, but the odds are you're doing LinkedIn. As a matter of fact, I got this job because of LinkedIn. One of the owners found my LinkedIn profile and sent me an email and said, hey, I need a distance instructor to do some of the things that it looks like you're qualified for. Are you interested? So I started doing things there. So when we connect to the network, what are we doing? And I guess we're talking about what network are we connecting to, depending on what we want to do. You may want it if you're a Facebooker. I'm not. My wife is, but I mean, she's got all these Facebook friends and they share information. And that's what networking is all about, is sharing information, sharing resources. But we've got to have some kind of particular configurations, devices, protocols, languages in order to do that. So what does it mean? We may want to be opening something on a file server. We may want to get to a document in our home directory. You may want to get to a Dropbox folder in order to get some information. You may want to get to a website that's got, study questions for your certification on it. You may want to print a document. Those things. Connect to the intranet. The intranet is the internal network. In a lot of places, a lot of locations, and I didn't say I was a network administrator a couple places too, but some training is done on the intranet internally because you don't want it to be available to the public. So you make those particular resources only available internally to your employees. So intranet within your own network, and internet, obviously, the great big network that we send information around the world with. The signal from a phone, voice over IP. A lot of people have gone to that. We use the network in order to do phone calls, or you may use a Skype or something like that for a phone call. So we're using the network, a network, for voice communication. Lots of different things here. The key here in connectivity is remote system. We're connecting to a remote system. If it's on our individual device, we don't need a network. And by the way, if it's on our individual device and not connected to a network anywhere, it's probably going to be pretty secure. When we get into the security, what causes that is this same connectivity, the ability to get to remote systems. The connectivity, the conditions, and we got to have, and I always usually say three things. We got to have something that somebody wants, something that somebody has. I guess we have more than that. We're going to have four. Something that, a resource, and then somebody's got to want that resource. We're going to have some sort of a connectivity, some sort of a media to get there, and this physical connection could be wireless. It's going to be the media. The wireless is the atmosphere is going to be our physical media. Able to transmit and receive information, we have to have an address, some way to get to or some place to go to this thing. And then we have to recognize and act on the data. We have to have a language, and the language is going to be the protocol. So we have to have something that we want to get, and somebody's got to have it. We got to have some sort of connection to get there. Could be a piece of fiber, could be a piece of copper, could be a wireless. In order to do that, the media that we're going to use, it's got to have an address, and that's the one thing that I have not typically put in mind. But you got to have some way to know when you got to the right location. That's going to be an address, and we're going to have two different types of addresses when we get to talking about addressing. And then we have to have a common language. It's just like if we were here on this class and I was speaking Chinese and you were speaking English, probably wouldn't do you a whole lot of good. And that's what the common language kind of thing is about. Common hardware and network standards are required. And we have gotten to standards, and I'm sure that those who had A+ talked about standards. Why do we have standards? Because then, we can have a whole lot of manufacturers, for one thing, to make things. That's not always been the case. In the early days, if you had a compact and you wanted to upgrade it, you got to get a compact device in order to do that. If you had a Dell, you had to get a Dell device. Now, if you wanted, you go to Amazon or to one of the vendors and say, hey, I wanted this, and say, okay, it meets this standard. You can get it for a lot less than other things. And this one, network components, and the first couple here, and I like to scroll on things, is node and host. And I think that this is something that's kind of here, it's splitting hairs. A device that actively transmits and receives is a node. And here a host has a beginning and an ending point. Okay, so why do we do this? And I guess it makes great test questions. A device that actually transmits and receives: a computer, network printer, storage device, network device like a router or a switch, could pass through multiple nodes. If we had a router, for instance, and if you do a trace route, and that's one of the troubleshooting things that we'll talk about, it tells you how many routers you go through. So, and routers are typically represented by circles. So when I do that, that's router. So if I'm going from point A to point B, I might have to go through a dozen routers in order to get there. And this is why it could pass through multiple nodes. So a router could be a node, would be a node in this case. A host is a beginning and an end point, must have an address, and not all nodes are hosts. And we'll go through a lot of, and I think around the world thing, but must have an address, a beginning and an end point. So we could say a computer or a server, right? A computer or a server would be that. A computer, hey, it's a beginning point and an ending point. Beginning point, we go get information that comes back to us, it's the ending point. These devices that we store information on, it's a beginning point and an ending point. So host, and I guess that beginning and ending point are the keywords for host. And then a device actively transmits and receives media, the physical path, including wireless. The media is going to be, fiber. Fiber is what we all want, but not always so simple to put in. Could be copper. And the copper that we use now is twisted pair. Although we'll talk a lot about coax and see pictures of coax. It's used in cable modem, but it's not used in networking itself that much. And then wireless. Wireless is the easy to set up, not always as secure as we would like it to be. And the data is the information that can be carried on the media. A bit is a binary, it's a 0 or a 1. The advantage to binary, 0 or 1, it's either there or it's not. It's on or it's off. It's kind of like a light switch. It's a binary thing. You turn the light on, you turn the light off. Network device, part of the network structure, not a host or network device. Maybe we'll identify some of those as we go through, but some terminology for these things. And this is one that I actually just said, hey, maybe we should get some pictures of some of these things and put them in here. So we have nodes here, special purpose devices. We have the PC, the server, the switch, bridge, router. A switch, we said we were distinguished between a switch and a router. So let's distinguish a little bit and we will do more. A switch is a device that we plug our computers into so that they can communicate with each other. And we're going to talk about some different domains, and one of them is going to be a broadcast domain, and one of them is going to be a collision domain. But these guys, as long as they're all on the same IP network, are all going to be able to communicate with each other. So a switch is a kind of maybe a junction point for a lot of different devices here. A bridge we'll talk about. A bridge is just kind of separates some things, and then a router allows us to route information to get from A to B. Routers are the things that allow us to go to google.com or cisco.learning.leaderquestonline.com or ecpi.edu. But those are the things in the Cisco ad. I don't know if they still do it, but the Cisco ad. The internet runs on Cisco routers, so the routers get us from there to the other. And then the links, the connections between nodes, fiber, coax, wireless, and then I added the wire in here today. Some symbols that you will see, and these are kind of the Cisco standards. A router here, a circle, it's got a bunch of arrows on it. I don't have time to draw the arrows. A wireless router, and that may or may not be the symbol that you see for wireless. Usually you're going to get something like this that represents the wireless portion of it. A bridge is there. A switch has got arrows going out in both directions. A hub, and we'll talk about these devices. The two arrows, a wireless access point, which is a little different than a wireless router, and we'll distinguish between those. A wireless bridge, which you might see with those things. So the symbology that you might see for the devices themselves. So when we do networking, we said physical versus logical networks. A physical network is, in fact, what we see. The NIC, the cabling, the hardware, signals are still part of the network. But in my first network, we had what's called a true bus. And we're going to talk about the bus topology here in a few minutes, but we might as well introduce it now. Which is basically a piece of coax that had T connectors on it that connected to the computers. So we had this coax. So, hey, it's a physical and we called it a bus. What we saw was a physical bus that ran from one end to the other. So we connected all of our machines using this coax, and it was a physical bus. When we look at this, the topologies we have we will do those. They're not going to be that many. The bus here, just everything connected to the same piece of wire, basically. What you see, the NIC, the network interface card, where we plug the cabling into, the cabling itself, hardware. Signals are part of the network. We don't really see those unless we put an oscilloscope on it. We can see those. A logical network is the way the electrons. We can have different physical and logical networks when we do those things. A node, for instance, is defined by its address and not its location. Physical location. Is it on the third floor? I don't really care. What I care about is its IP address, its network address, how to get from one to the other. They're related. The physical network can have multiple logical networks and vice versa. And I think this is right out of the book. In a logical network, the repeater doesn't exist. The repeater here, and a repeater, and I'll say this probably several times, but a repeater is not an amplifier, because these networking media are not perfect. So we generate noise in them. And if we get noise in the media and we amplified the signal, we would amplify the noise along with the signal. So they repeat. Kind of handy, since it's going to be a 0 or a 1, that we can pick them out and bring them back by repeating them. By repeating them, we bring them back to the original signal so that we can then degrade the signal some more and do another repeater. A logical network here, the way the data flows, the repeater doesn't exist. But in the physical network, it obviously is there. It's a node in the physical network. So logical is electron flow, and physical is what we're going to see. But the electron flow, the electrons, as we go through here, and what would happen when we do, we start at a signal level and it gradually degrades. The repeater is going to pop it back up till it degrades and it gets over here, and we can make it work at the other end. So different ways, and this one is about some of the different ways that we can these ways. The other one here, network challenges. Availability. The ability to maintain reliable connectivity. No unplanned outages, or not having unplanned outages. I've had a couple of them while I've been doing these courses. Sitting here and just talking away, and all of a sudden the lights go out, or the network goes down, the internet goes down for whatever reason. May happen when we do these things. If it does, just immediately go to labs. But availability, unplanned outages. Somebody in the early days, people would have a switch on the light switch that goes, the outlet was on the light switch that goes to the overhead. Plug the server in there, and said, and the problem was the server goes out every night when we turn the lights out. Availability, the ability to keep running. Reliability. Availability is that it is running. Reliability is that we get the information. No communication errors, no errors on these things, no choppy videos, no bad phone calls. Serviceability, how easy is it to perform maintenance? And if you've ever worked on your car, you can appreciate the serviceability, because the part that you need to change is always the one that you just can't. So how easy to perform the maintenance? If it's easy to perform the maintenance, we're going to have shorter outages if we have them, and a higher availability. And that's the objective to do these things, is high availability, high reliability, good serviceability, performance to rapidly convey traffic, throughput, and latency, how long to respond. Latency is the delay in signal, and deployed, and you guys may have experienced that from long distances, that you say something into a phone or radio, and then nothing happens. How long did it take the signal to get there? We used to have DirecTV, and if I were watching the game it was on locally, I could watch the kickoff on the regular TV, switch over to the DirecTV and watch the kickoff again. That's the delay that we have in these things. And distances are going to cause security, how hard for unauthorized users to access the information. Scalability, how growable, how easy is it to increase the size of the network in a logical, managed method, not just random, let's put this here and put that there, which is the way a lot of them do. Compatibility, the ability for all components to communicate. Are the protocols, do they all support the same protocols? The things that we do there. And then the quality of service. Quality of service is the ability to give some things, voice and video in particular, a higher priority. Because if you're opening a web page, your web browser probably doesn't care if it's delayed by 100 milliseconds. The phone call could care if it was delayed by 100 milliseconds. So we can give certain traffic a higher priority than other traffic. So this worked out really well. At the end of each of these are some questions which we'll do, and you can answer them in the chat when we do these. So as we go through them, and if you've got the PowerPoint, you've got the answers there anyway. But what sort of device may or may not be a host depending on the context? D, a workstation. B, a printer. Anybody else? See, if I had my questions, I could mark the answer, but I don't. It's going to be a printer. And that's what they say. Don't have an E. C, a switch. They say a printer. And if we go back to him, a device that may or may not be a host. And a host was a beginning and an endpoint, right? And this was just a device. Personally, I would have picked switch, because a switch is a place that is a device here, not a host. Could be a host if I'm configuring it. I go to it to configure it. It's an endpoint and a beginning point. It's simply back to say, yeah, I got it done right. But printer is the answer that they wanted on that one. That's the one that's kind of odd. The physical and logical network can't be totally separated from one another. True or false? False, true, true, true. We'll go with true. They are going to be related, and we're going to look more at those as we go through this thing, how that works. What quality should a high-performance network have? High latency, low latency, high scalability, high throughput. A B and a D. Low latency, low latency, and high throughput. So we've been going for about an hour. So the next thing that we want to look at is classifying network scope, topology, resource sharing model. Scope is how big it is, and we know that some of them are bigger than others. The one in your house is not as big as the one that LeaderQuest uses, for instance, or even the one that's within the building that you're in at LeaderQuest. So scopes is the physical extent, not in the number of nodes, but how far apart they are. And we could have something that didn't go very far that has lots of nodes. And you notice we're using nodes here. And I think that they're going to use, I know they're going to use, those two terms interchangeably. So for question purposes, kind of distinguish it, but a node is something on the internet, something on the network. A host is something on the network. So we have those things, we have the terminology, and then it gets mixed, and I didn't try to change all those things, but how far apart they are. Are they in, I'm in Wisconsin, or in Wisconsin and Jacksonville? Are we in Jacksonville and Colorado Springs? I think that's where most everybody is in this one. No, or Dallas. Yeah, we got some Dallas too. So different locations. Where are they? Small office, home office, Soho, single room or building. Small office could be in a building, and usually, like a house that maybe has 4 or 5, up to 10 or 12 devices, we'll say, on them. A major service provider could have could be a country, and different scopes are going to use different technologies. The terminologies and I'll tell you, when we're going to talk about this thing called the OSI model later, the differences, the technologies that we're talking about only exist, the differences down at the lower levels, because if you use a web browser, a Chrome or an Edge or Opera or Firefox or whatever, whether you contact a website in your house at Jacksonville, at Dallas, at Colorado Springs, or whether you contact a web browser in Hong Kong, they all use the same HTTP protocol. The way that we get it there is going to vary depending upon the technology. A lot of things are the same, different. Local area network, and this is one that we kind of, and we'll do it this way, and then we're going to look at the real definition here in a little bit. But a local area network is confined to a fairly small area, usually within a single building or maybe a group of buildings, maybe a single room, maybe a group of rooms. I don't know, I really don't know how. I know how we had it divided at ECPI. We had rooms and different areas, and each of them was its own local area network, and then we connected all these things together with a router. So routers are going to be required to connect these things together. So an area or a small area are numerous. And when we get to the wide area networks, the WANs, which are going to be next, the WAN connects LANs. LAN, local area networks, what you and I have. Offices, schools, homes, could be wired or wireless. Complex or simple. And if you have a lot of stuff, this thing up here, this whole area, different IP subnets would be considered a LAN, although I said that each of them was a LAN, and the whole thing's going to be a LAN that we connect together. How complex is it? How many devices do we have? Are we using virtualization, for instance, to make it a little more complex? Complex or simple? Normally connect to larger networks, and those larger networks, we'll say WANs. We're going to have a couple of other things that are in there. We could also have this thing called a MAN, a metropolitan area network. Usually simple, inexpensive technology, and usually Ethernet. Okay, we introduced the term here, Ethernet. And I've talked about this model. When we get to the model, we're going to find Ethernet is going to be at layer 2 of it. And don't worry about that. We're going to get to the model. Ethernet is how we connect it. We say Ethernet. Ethernet is a technology. A lot of times we talk about Ethernet cable as twisted pair. Twisted pair is the type of cable. Ethernet is the technology that we use together. Ethernet, high speed. Pretty high speed. I mean, we can go to like 10 gigabits per second. Should be a small b. Small b's are bits and big b's are bytes. 10 gig, and if I look at my WAN connection, it's 200 megabytes per second. So megabits per second, not megabytes per second, megabits per second. So it's going to be quite a bit slower. Usually the LANs are going to be the fastest of all of the networks. And some of you had A+, and it's kind of the same thing there. How fast is the processor? How fast does the processor work? How fast does the memory bus work? I mean, we're talking enormous speeds here, but we're talking about little bitty short distances. In a network, a local area network, we're usually talking in distances of 100 meters for copper. So we're not going all that far. When we're talking about wide area networks, we're talking about going around the world. So different speeds, different technologies. The next one are some images here, local area network, just kind of different things, and try to, I guess, get some of the devices introduced here also. We have the switch here, Ethernet switches that connect all these devices together. It's a point that a junction point. I don't know, junction point is a good term or not, but it's a place that they all connect to so that they can communicate with each other. We have PCs, a printer, we have a server here, different things over here. That's another picture, and then the switch here with the symbology that we use, and then here the switch. This says a network interface device, a NID. Something going here, and let's say that we're going to have a router here. If we're going to the internet, we're going to have a router to get us out of this thing. A Wi-Fi router to connect our mobile devices, and I said you're usually going to get a little bit of a symbology here of some sort when we're talking about wireless, so that you know that it is a wide area network, large area, nodes in multiple cities or countries. I expect, and I know at ECPI, and I will mention them because I was a network administrator there for some time, and I taught there for almost 20 years. But we had wide area network that each of the campuses, and I think there were 15 at the time, campuses all connected through a wide area network to the headquarters activity, so that we could send information to the headquarters activity. And if they wanted the different locations to communicate, we could go through the headquarters to connect. Could be, and they were in multiple cities. I was in Roanoke, the headquarters in Virginia Beach, had a Charlotte campus, Greensboro, Portsmouth, Northern Virginia, Greenville, South Carolina, all sorts of different places connecting together over this wide area network. A LAN typically owned by a single entity, a LeaderQuest. LeaderQuest owns their local area network. A WAN uses, and it says lease lines, maybe the internet, using VPNs, a term that you probably heard, a virtual private network. But we're using somebody else's resources, not our own. We typically are not going to be able to, let's say we're going to go out and string our own cable from Roanoke to Virginia Beach. That's not going to happen. And it'd be really expensive anyway. So we lease or rent space, channel space, communication space, from a provider that has all of that infrastructure in place. So the technologies are designed to be used over long distances when we do those things. There is here's security issue, because we're trusting a third party with and we typically not going to have a whole lot happen there, but you read about things that happen on a daily basis from somebody that we trusted our information to, a trusted third party. They compromised your credit card. They compromised and in my case, it was the U.S. government compromised my information when they had the hack on the personnel system to do those things. So sending information to over a trusted third party's lines, it can happen. It's not as easy as we make it sound sometimes. But some of the technologies that are used here, DSL, digital subscriber link, say, oh yeah, that's something that I don't want. I got a cable modem, and if you can't get a cable modem, you get DSL. But frame relay, an older technology, PPP, point-to-point protocol, which is a really older technology. It was the technology that was used when I used the dial-up modem, but we're still using it because it works. WiMAX, which is long-range wireless, MPLS, multi-protocol label systems. Right now, this is just a bunch of letters. That MPLS, if you do CCNA, we'll look at how that works a little bit different. And the objective here is we're using different technologies for the different types of networks. We used Ethernet. We had Ethernet there for the local area network. The other thing that we could have is a token ring. We're going to look at the topologies in a few minutes. But we have to have something that allows us to, and we'll introduce a new term here, encapsulate, wrap up the information to be able to send it from one location to the other. Wide area network, and what this is showing is that we have a bunch of local area networks that are connected here over different areas. We have Seattle, Toronto, and New York. This is a LAN over here, a local area network. This is a LAN over here, a local area network, and a LAN. So a WAN, a wide area network, connects local area networks together. Can connect local area networks together. It can connect us to the internet, which is to a server someplace, which is going to be on somebody's network. It's going to be in a data center somewhere, or in a room in a building somewhere, depending on how it's hosted to do those things. So we're going to go from one to the other. Some other scopes, and I put some images in here to maybe kind of make them seem a little bit more realistic, but a campus area network, buildings in a single campus, and that's the one at the upper up there. It's like a LAN, but it uses longer distances, and it basically uses LAN technologies, but we're going to use different media than wired. And one of the things to kind of put in the back of your head, if you're taking notes, take a note. If you have distances, wired or copper is typically going to be able to go 100 meters. I say typically, it's not always going to be the case, but if you're asked a question, you know the answer, and it's got 100 meters, it's a good guess. Not 100 feet, but 100 meters. So like a LAN, but it uses longer distances. A metropolitan area network is something that connects a city together, and the city basically owns, or somebody owns, the infrastructure downtown that uses, again, its own technologies to connect these local area networks in a smaller than the world, but bigger than our building or our set of buildings. Personal area network, you probably already do that. If you connect a Bluetooth to your phone, a Bluetooth headset, or a Bluetooth speaker, or if you connect something on a USB port. Personal area network. Again, much shorter distances. Bluetooth, USB, different things that are going to be used there. Near field communication. When we see near field communication, think payment. I mean, that's what we're really talking about, payment via phone. It is measured distances in centimeters. Is it absolutely secure? No, because if somebody can get something between your phone and that payment station, different scopes of what goes on. Topologies, and they've got some in here, this line up here, which I guess, I will admit, I have never seen a line topology, and this is the topology is how the nodes are connected together, the network shape. A line topology, single connection, one system to the next up here, which is kind of what this one shows here, but one to the other that connects in a line with these things. Each of the topologies are going to have advantages and disadvantages, and they can be a physical topology, what we see, or a logical topology, the way that the data flows, the information flows from one site to the other. The simplest, a point-to-point topology. This shows a workstation to a desktop PC. We connect two computers together, NIC to NIC, and when we do that, we're going to have to use this thing called a crossover cable. I know I'm introducing a lot of terms, and we will get to those, so hopefully we're going to hear them again as you go through. But the simplest network, a single line joins a station, one station to the other. Point-to-point is something that's used in wide area networks also. Point-to-point, if we have two routers at two different locations and we connect these together, this is going to be a point-to-point connection, and it uses a point-to-point protocol, PPP, point-to-point protocol, to use these things, can use that. And on the back side here we would have our LAN, and we would have our LAN. So we have point-to-point connection, the simplest, two computers with Ethernet, crossover cable, could be used with the line topology, connect one to the other. Could be used to connect two sites together, two different cities together, two different anythings together. It's going to be used. A bus topology solves the line problems because in the line, and this looks the same, right? It looks the same. In the line, we have the devices are actually connected together. In the bus, the devices are connected to a common piece of media. And when we do that, the media here is going to be coax. So shared cable called a bus. And this is the one that we connect these things together with T connectors to these things. And we use a BNC connector, the quick disconnect connectors, to go into the bus. The coax goes from one to the other, and we have computers on these things. When we do this, you notice that if you will look at this, if this guy wants to send something, everybody can hear it. And that's one of the things, characteristics of a bus. Good, bad, or indifferent. It's just one of the characteristics. Shared cable called a bus, all share the same media, and the NIC looks for the traffic. Boy, that sounds really strange, doesn't it? The NIC looks for the traffic to it. How about to it? To it, and it's going to use a special address, an address. And again, we're going to revisit these things. An address called a physical address, which is going to be unique. Believe me, that's unique. Which is also going to be called a MAC address, which is going to be a 48-bit address. Lots of characteristics to this. Looks for traffic that's addressed to it. But what happens is it's burned in at the manufacturer, and we eventually find the MAC address and send the information to that MAC address. And these guys, even though they can see everything, they only accept the traffic that's to them. I guess we'll say they're kind of honest, except when we get somebody in here who's not so honest. Big problem with the bus is everybody. If it's busy or off, it doesn't affect other traffic. If it's busy and if it's busy, we'll wait till we get to the OSI, and we'll talk about how this thing works, how you actually get access to it. But you look at it and say, hey, if somebody is using it, kind of like if you're driving on a highway and you come up to a one-lane bridge, if somebody's using that one-lane bridge, you can't. If you do, you're going to have a collision. Same thing's going to happen here. If somebody else is using it, we can't. So it's not going to be all that. Bus topology, some characteristics here. Each end must be properly terminated. And that, I put that in. Somebody has had that question. Somebody asked the question, why do we have to do that? And what is this terminator business? If we have this bus here with our T connectors, and I'm not going to draw very many of them, at the end we have it's a 50 ohm resistor. And what that's for is that when the signal gets to the end, it doesn't get reflected back into the media. Antenna theory and all that things, depending on what the length, it wasn't necessarily, but it could get reflected back and just cause noise, cause issues there. So we have this terminator, which is a 50 ohm resistor on the end to prevent signals from reflecting back, to absorb excess signal. It's just a simple resistor, but it means a break anywhere in the bus can cause a termination failure and host the entire network. That was another problem we used to have because we had students, obviously. Students being students, I said I'm going to do this, but we'll draw some more T connectors in here. We had, in one of the lab rooms, I think we had 4 media runs. And what the students would love to do, the B and C connectors, a little quick connect, turn it on, snaps on, is as they would leaving, just so they could entertain us for the afternoon, would back off the connector and one of the T connectors just so it didn't have an electrical connectivity. When that happened, nothing works on this bus. So a break anywhere on the bus is going to bring disconnecting a device from the bus as opposed to just turning it off can also cause a termination failure. That's straight out of the book. I worked on one of these things for 4 or 5 years, and disconnecting the device here from the NIC never did that to us. If we took it out from one of these things, one of the T connectors in the bus, it absolutely would do that. If you didn't have a terminating resistor, it absolutely would not work. Only one node can transmit data on the bus at a time. The total throughput must be shared by the entire bus. And that kind of makes sense, I hope. That when we have all these things connected to it, all of these people trying to get on this one-way street, that once I'm on it, you can't get on it because I'm going to take the whole thing. I'm trying to get a different color here. I'm going to take the whole thing. So I'm driving down the street. You're going to have to wait until I get done driving down the street, until my data has cleared. Then you can get onto it. And then the next person can get onto it, but one at a time. So as you can see, that's going to be kind of slow. And when you do this, it's going to send it in both directions so that nobody can get onto it. The total throughput must be shared. This isn't a problem on a small network with limited traffic. Yes, it is. But larger and busier the network becomes, the smaller each system's share is. And we're going to get collisions in these things. And this is going to be called a collision domain because we have collisions in it. And when we have collisions, we have to go through a timing process that we say, oh, I had a collision, I got to wait, got to do a back off and go through the whole, and we're going to call it CSMA, carrier sense multiple access. We're going to listen on the media to see if there's any information on it. If there is, we're going to wait. If there's not, we're going to put our data out here. But if this guy over here doing the same thing puts his data out there, we're going to have a collision. So it's going to be reported with a jam signal. And the jam signal is going to say, hey, we had a collision. So I'm going to go through this, listen after a random back-off period. I'm going to go through the process. I'm going to listen until the media is clear and then try and sending my data again. And as you can imagine, just like on a busy highway, 2-lane highway, 1-lane highway that has multiple accesses to it, the busier it gets, the probability of a collision increases as the amount of traffic increases on the highway. Same thing happens on the network. No central control. 2 nodes might try to transmit at once, interfere with each other. This area is called a collision. Protocols like Ethernet can detect. It says correct, and this is straight out of the book, detect and correct. It doesn't correct the collision. It detects and reports the collision. Because once you have a collision, it's like saying, okay, I had a collision in my car, so let's correct that. You can repair the damage. We can repair the damage. We can report the collision. We report it to the insurance company. They would repair the damage. And that's what happens here with this random back off and then redo the whole thing. Consumes time, reduces performance. Large busy networks are more collisions. And again, hopefully that if you think about it, if you think about this data flow, data traffic, very similar to getting in a car, getting on a highway. Or do you have a two-way? We're going to do this thing called half duplex. Do you have not a divided highway that goes up to a single lane bridge, which means that we can go in both directions, but when we get on a single lane bridge, hey, only one of us can go at a time. That's what a bus is. Suffers more collisions. Troubleshooting is difficult. Since an error anywhere in the bus can impair the whole network. It's not difficult, but it's time consuming, depending on how many nodes you have. And we have this, and we have a break in it. We'll just draw this big thing here. What you do, because I've had to do this, is you go to the middle here and you take a T connector apart and you put a terminator on each end, and whichever end works, that one's good. Then you go to the one that didn't work, into the middle it, do the same thing. Keep dividing it in half until you get to there. A point to multi-point system. Point to multi-point, one point to multiple devices side of this thing. A ring topology, token ring, it's a little bit better. But problem with the ring topology is what happens is, they say all nodes are a continuous circle, and that's exactly, this is a physical ring. Physical ring that goes around this thing, data transmitted in one direction. Some rings do, in fact, have a second connection that goes around. It's called a counter-rotating ring, so that if this portion of it goes down, we can use the other one, and it would go in the data would go in the opposite direction. But this thing's called a token ring. Token, which has an electronic signal called the token that says when you get the token, you can put your data onto in the bus, we didn't have that token. In the bus, we just had to wait, look both ways on the street before we pulled out into it, and then say, oh, golly, I hope I don't have a collision. So it looks both ways, listens to see if there's anything going on, and then puts its data out there. Token ring, once we get the token, the electronic signal, we can send our data. It goes around the network until it gets to where it's going, and then that station accepts. And then when the token gets to it, it gets to put its information on. It gets access to the media. Ring advantages, daisy chain line. Each node on the ring has to process all the data that passes it. One of the things that is an advantage here is each of these points on the network is a repeater. So the signal gets repeated, gets regenerated, renewed, and so that we don't ever get a signal so degraded that we can't use it. Usually it's done with a single interface that has separate connections for receiving and transmitting. We call these ring in and ring out. So if I have a NIC here, I'm going to have a ring in, and it'll go over here and we'll have a ring in and a ring out. We'll go over here and we'll have a ring in, and then it'll go back over here to the ring in. So now we've created our ring, and we're going to pass the token to get access to the media. So separate connections. Collisions commonly avoided by using the token. A packet that circles constantly through the network and gives the owner permission to transmit, to access the media. So we send a token around to say, hey, you can send your data. You can speak. All the other time we're going to be listening. Has data to send, it waits for the token to arrive, then it sends data and the token forward. This can be, I guess, more orderly. I'm not going to say faster because it can be, we're going to improve our technology over the bus here in a few minutes. It can be relatively slow, depending on, again, how many devices are in the network. If we have 3 here, not so bad. Let's say we've got 100 in this single ring, or let's say even we have 20 in a single ring. That's a lot of devices to go through before you get to all the way around. Maybe before you get to. I guess the thing would be that if you, because this guy's right next to you, if you're sending it to him, you got to go through the whole ring in order to get there. And then the answer comes back. It's more fault tolerant than a bus since it doesn't rely on terminations. It doesn't rely on the carrier sense multiple access and the collision detection. We're not going to have collisions in this thing. Counter-rotating rings can correct for cable failure when we do that. It's easier than on the bus because these things, these bus connectors, listen for their nearest upstream neighbor. And if they don't get a signal, don't get something from data sent from the nearest upstream neighbor because it's in continuous motion, it'll report it as a problem. That there's a problem in the network. Disadvantages, single rings, single point of failure. If it breaks anywhere, then the entire network goes down. More cable than other topologies, depending on the physical locations of the nodes. The directional nature of the ring means that each node is placed in a certain order. It can be complicated to add new nodes. It is more difficult to configure a token ring than it is an Ethernet. If we want to add a workstation to Ethernet, we just plug it into the switch. Token ring, we've got to enter it into the ring. We've got to put it someplace in this ring. A star topology, most popular, and this is the one where we use switches. A star topology up here, I say hub or switch. Hopefully you'll never see a hub in your networking days. And it's going to be a switch is a centralized location that all the devices connect to. The reason they call it a star is because they say, oh yeah, we'll set this thing in the middle of the room and everybody will connect to it and it looks like they're going out in a star. But what usually happens is we set it in the back of the room and then we have all of our machines up here and we have to run cable to each of these guys, but it's still a star topology. A broken cable only affects one node. If something happens here, it only affects this particular one, not everybody else. If we turn the power off, it's going to affect everybody else. A failed hub will bring down the entire network. Can minimize the risk by making sure it's robust and easily serviced. And the easily serviced is spares. And these are devices that you could have spares pretty readily. And it's how difficult is it? You unplug all of the RJ45s here, put the new one in, plug them all back in. You ought to be back up in 5 to 10 minutes, depending on how long it takes you to get the new device from the storeroom. Connection. Every connection is point-to-point, easy to isolate the problems. The size is limited by the number of physical connections, and we can get some pretty big ones. The standard switch is usually going to be a 24-port. You see a lot of those, but you can have some that have hundreds of ports on them, depending on how much you pay. You can link hubs together to form a large tree topology. And we'll talk about hubs here in a second. I think I got another one here I do want to talk about hubs and how many you actually can connect. Hubs is the early Ethernet network, and it is a true bus topology in here. When we use them, let me look and see what my next talk about this stuff here. Now we'll talk about logical topology in a little bit. We'll talk about flows here in a little bit, and we will discuss that then. But we can have issues with the star topology, a centralized device. Single point of failure. Sure, there are lots of single points of failures in networks. You can't do away with all of them. A mesh topology connects everything to everything else. Every node is directly connected. And you say, yeah, that really sounds cool because not a big problem. Lots of redundancy, lots of pathways, no delays. The problem is n times n minus 1 over 2 is the number of connections that we need. If we have here the 4 times 3 over 2 is 6, and I think that's what we have here. 1, 2, 3, 4, 5. Not so bad. Let's say we have 10 devices. Not an unreasonable number, which is going to be 40. So it can get unwieldy pretty fast. Usually our high value units are going to be connected using a or a mesh topology. Each node to communicate with multiple nodes at the same time. Advantage here, this connection goes down, I can still get there. I still have multiple paths to get to from one location to the other location. I could go this way. So multiple communication paths is a really big advantage of this. Difficult to implement because of the number of connections increases exponentially with the number of nodes using that formula. Used to provide reliable communications between independent networks. Reliable communications, high value units are the ones we're going to do this. Hybrid topology just simply means that we use some of the different topology types. Exhibits characteristics in more than one standard. Put this picture down here. So we got a bus, we got a star down here, we have terminators, really big terminators, a ring, so characteristics of different ones. Each section of the network follows its own rules. Can be complex to maintain. Anytime you start mixing even vendors, it's going to be more complex. You're going to need more training. You're going to need a higher knowledge level because they all work a little bit differently. Most large networks, several smaller subnetworks, and each subnetwork may have a different topology. And in today's world, or at least in our world, all of our smaller topologies were a star using fast Ethernet. So we didn't get into all of these other ones when we did there. The types of hybrid topologies are star, bus, star of stars, and then the star ring, different things. Star of stars is when we connect a bunch of different star topologies together. If we have a switch here with this thing, and then here, and then here, and then here, we have a star here, a star of stars, and then a bunch of different star topologies. Topology summary, some images. We have the ring, the mesh, the star, fully connected. The mesh, that's what I call a partial mesh. Partial mesh because some of them are meshed. This guy out here is out of luck. I mean, if something happens, they only got one way in. And then we have the star, tree, the line, and then the bus. This, to me, and this may be just to me, but this is the true mesh. Everything's connected to everything else. So different images, what the different topologies. We can have a logical topology. And the logical topology is the way the data flows. And I said we would do that in a bus, in a hub. A hub is a logical bus in a physical star. How does that happen? Well, if we have our bus here that has all of our stuff, and I'm not going to try to draw T's, connected to it, if we put it in a box and shrink it and connect it with RJ45s, that's a hub. So we have our physical star, but internally it's still a bus, and everything sees everything else. You can have a token ring. There actually is a token bus, but we don't really talk. I don't know. I've never seen one. I don't know if anybody uses it. Technology issue when we do these things. Switched Ethernet is the most popular. Switched Ethernet doesn't have collisions. Switched Ethernet uses, and we'll talk about switches, uses special technologies on switches to only send the data to the correct location. So switched Ethernet is going to be the most popular, which is going to be a star in a token ring. And I think in your book it says that it can't be you can't do it this way. You can. It's called an MAU, a multi-access unit, that we have connections on it. We have our ring in and our ring out, connections and goes around the world, ring in to ring out, ring in to ring out, and then we bring it back around to the ring so we can have a ring in a physical star and a logical ring. So we can have physical. Again, physical is what it looks like. Logical is the way the data flows. Logical topologies, and this is, I think I copied this right straight out of the book, a switched Ethernet, typical modern LAN. The box is a switch, a logical node with the ability to actively direct traffic to prevent collisions. And it's going to be, and again we'll talk about this, just I guess maybe a preview of it. It's going to use this thing called a MAC table. We said a little earlier that we had this MAC address, which was the physical address, which was the unique address, and in the switch it has this MAC address table, which has the MAC address, we'll say the MAC address, and then the port that it's associated with it. So when data comes in that has this particular MAC address, it just sends it out that. So it is, and this is all connections of the switch are independent. The logical topology is also a star when we do those things. Go ahead, Lisa. You unmuted, but I can't hear you. Okay, maybe not. Thought you had a question, but if you do have a question, please ask. You can put them in the chat, or you can just in the chat. I will eventually see it. I might not see it exactly at that time. Older Ethernet. The box is likely a hub. The shared Ethernet, the one we talked about, that everybody is in fact sharing the same one. You know, the switched Ethernet would be nice if we could have highways like that, because we'd all have private highways. That's not a problem. Private highways, and we wouldn't have collisions, and we wouldn't have a lot of problems. We wouldn't have to wait, because we would have our own dedicated highway to get everywhere. Impractical, but we can do that in our networks. Token ring, the LAN using the once common token ring. Standard, the box is a multi-station access unit, a MAU, MSAU or MAU. I've seen both of these. Seen it listed both ways. Also passes data in the order of sequence from one port to the next, just like it did in the physical. The shared Ethernet, the switched Ethernet, the shared Ethernet is any of you that have ever worked on one. We had one. We were doing these things one time, and I thought everybody was back on the switch, but one person wasn't. We were downloading something from a server, and it's going to take him like, I don't know, 30 minutes to get it, and everybody else got it in 42 seconds or whatever. So a switch is the thing that you can do to really help out. Some images here. Shared Ethernet, the hub, the switched Ethernet is going to be the switch. Kind of, I guess the switch could be a tipper there, huh? And the MSAU, the multi-access unit, showing the ring in and the ring out, that we can have a token ring that is a physical star and a logical ring. Resource sharing, when we want to share information or share resources with things. Anything that we want to access on the network is a resource. Printer, we want to print a document. We want to get to a web page. We want to get to a particular file on a file server. Resources are limited, but the resource is the thing that we're going to get. That's part of the what somebody has that we want part of networking. Each device can have a limited number of users, a limited bandwidth. We can limit what goes on, and in some cases the operating systems will limit what goes on, how many connections that we can have. Two primary models to do these, a peer-to-peer and a client-server model. A peer-to-peer is something that you and I would have at home. We have our computers connected to our 4-port switch and our wireless. Maybe we have some wireless out here too, huh? Connected to our wireless. If I have a resource here that I want to get from here, I want it here, I have to log in, I have to have a username and password on this device in order to get that resource. If I then want a resource here, and I got to have a username and password on this device. So the, I guess, manageability of this is limited to pretty small networks for peer-to-peer. Client server, we have a server machine. We have to have the server software, obviously, in order to do that. But we can have multiple users on a server, multi-users. So that depends on how much you want to spend and how big your network is with these things. Peer-to-peer, no central administration. All the hosts, and here host, node, host, back to hosts, are equal. A Windows workgroup, network to share resources. Windows workgroup or a home network, we want to share resources. Inexpensive to set up. All we need are workstations. More difficult administration, because if we're sharing these resources, everybody's got to have a username and password. Now, do you have actually, in reality, do you actually have those? I was working on a dentist's network one time, and they had this set up because he didn't want to buy a server. So they had a device, a workstation, that said, okay, this is our server, this is where our resources is, this is where our database is that we update. Everybody logged in as a single user in order to do that. Is that secure? Absolutely not. Was it effective there? Yes, because, you know, 3 or 4 people connecting to it. But it is more difficult to administer. Security, no central access control. Scalability, because, okay, we're going to change passwords, and we got a dozen of these things. I'm going to go to a dozen machines to change my password. A client-server model, 2 categories of devices here. Clients that request the resources and the servers that provide them. Centralized administration, because on the server we're going to have all of our users listed here. We'll log into, just like you did tonight, we'll have all of our users. Our users will be on the server. Just like those of you who logged in at Jacksonville, you logged in to an authentication server and you got on the workstation. We can now get to resources based on what this server says we can get to, what kind of authorization we have after we get logged in or authenticated. More expensive, we've got to have server software. And it does cost more than workstation software. More expertise to manage, a little bit more expertise. It is scalable, because then if I want to add a user, I just add a user to the list of users that can get on to here. Security is going to be easier because we have it centrally managed with these things. So 2 ways to share resources. The peer-to-peer and the client server. I know we're close to a break, but we're close to getting this one done. So let's do these questions and then we'll take a break. At the beginning, as a beginning network technician, what scope of network are you most likely to install or maintain? You got B, a local area network, and that is true. Order the following from the smallest to the largest. So which is the small? Start out with which is the smallest? NFC, network, near field communication network. What's the next smallest after near field? PAN, a personal area network. Don't you love these abbreviations? And after that is the LAN, and after that is the, there you go. She had them all there, and after the what did we get to? The LAN, CAN, and then let's see. LAN, CAN, MAN, WAN. All sorts of. So what do all those things mean? Near field communication, measured in centimeters. Personal area network, Bluetooth, measured in, 100 feet, 30 feet. I think 30 feet maybe is what they say. Personal area network, local area network, think 100 meters for it. Campus area network, I think maybe a couple kilometers. Metropolitan area network, however big your city is, and then wide area network, think worldwide. Identify each topology by its shape. So this one over here, the upper left is, we got a bus. I think the next one goes down here. These things always mess me up. What's the one under the bus? It's weird. It looks like a bus, but it is a line topology. And then the one here with the hub is a star. And the one down here with all of these connections to it is going to be a mesh. And then the one that goes in a circle is a ring. And I'm just going to do hybrid. That's the only one left. And yeah, different characteristics of the different ones when we do that. What topology would you choose when fault tolerance is the greatest concern? And we would go with a mesh on that. Most small LANs today incorporate both peer-to-peer and client-server elements. True or false? And we'll go with true, and we'll go with true. So let us take a break. Unless you have questions. If you have questions, please ask. When I confuse you, please say, you confuse me, you don't know what you're talking about. And let's come back at 15 minutes past the hour and we'll do the next one. This is kind of an overview relating the OSI model and the things that happen with it to sending a letter. All kind of understand what it is.
Reference model, or OSI model, describes the process by which data is sent over a network. The OSI model is divided into 7 layers. Sections are connected to networking software. The data to be sent is put into a packet that passes down through each layer, a private delivery through interoffice mail to a translator. In the OSI model, protocols maintain the connection between protocols at the network layer do the tracking and checking.
Again, an overview. Or yeah, I'm going to get to that. And Celeste, please do not throw sausage pizza away. I always had trouble with that. All people seem to need data processing. So please do not. And I've got one in here from Mike Meyer's book. Yeah. That does that. So that's kind of an overview of this thing. And then what does OSI stand for? Open Systems Interconnect. They actually were developing their own protocols, but they never did. This is a model. The OSI is a model. It's not necessarily the way that things actually work. It allows us to model the data flow. We'll talk about the TCP/IP model. It used to be called the DoD model. A little bit simpler, but it is the way that data actually flows. The purposes of the models, about the OSI reference model, and then about the TCP/IP reference model. Once we do the OSI, the TCP/IP is simple because it just say it does the same thing as this layer, same thing as that layer when we do that. But I guess the first one, and then some of these I've got repeated on the next slide also, is why do we want to use models? And the first bullet is it reduces complexity of a large problem to 7 smaller ones because it's got 7 layers. And this was back to, I said a little bit earlier, if you like, solving mysteries or puzzle solving, then networking is a place to be. And we don't have to solve all of it. First thing we have to do is figure out where the issue is, at which layer, and then we can troubleshoot that. The other advantage is the standardization. I alluded earlier that if you wanted to, and in the early days, if you had a compact computer, and compact got bought out, I think, by Dell. But if you had a compact computer, you had to go buy a compact NIC if you were going to go on the internet, on the network. If you were going to have a Dell, you had to buy a Dell NIC. But what this does is allow standardization. Now, if you need a NIC, you just go online and you buy a NIC. One that'll plug in as long as it's got the proper bus plugs on it. You can plug it into your motherboard. You can use it. Prevents changes from a layer to affecting other layers. We had a little question a little earlier about IPv4, how much is on the test, and I guess some still and keep saying, and yes, they've been saying for years, probably about the last 15 years, that IPv6, the switchover is imminent. Well, the switchover is happening. My ISP, I got an IPv6 address. I have an IPv4 and an IPv6 called dual stack, where both of them are being used. But if I can get somewhere using the 6 version, it's going to use the 6 version because it's a lot better protocol than the 4 version. But what that means is that as we're transitioning from the Internet Protocol IP addressing of the version 4 to the version 6, the only thing that's affected is the networking layer. We'll see that in a minute. That's where those addresses are. Only the layer where those addresses are going to be affected by it. Excuse me. The 4 layers are concerned with shipping data. And if we were doing the CCNA, the Cisco class, I'd say, and that's what we're concerned about here, is getting from one to the other. We're concerned about the entire network in this class. So we have to worry about the upper 3 layers also, deal with applications that are running on the end devices, the web browsers, those sorts of things. Applications in networking are, think of them as services and not, an application in networking is not Microsoft Word. It's not Excel. It's not any of those things. It's a web server. It's a mail server. It's the HTTP connection from the browser. It's services. It's not the things that we would type on for those things, programs that we would run. Multi-vendor interoperability, kind of referred to that a little bit earlier, alluded to that. Products that meet the same networking standards are going to be able to communicate with each other. And then modular engineering. One vendor can write software that implements higher layers, for example, a web browser, and another can write software that implements lower layers. The TCP/IP software that's built into, it says Microsoft, built into Linux also. We have those things. And then this is again that the layers themselves, and this has got the OSI on the left, the Open Systems Interconnect, and the TCP/IP on the right. What we do is group some of the different layers together with the TCP/IP to do the same function that would happen with the OSI. Again, the benefits less complex compared to not using a layered model, standardized interfaces. This is easier to learn, and at this point you can really say, what do you mean easier to learn? Once we've looked at it, and I'll try to keep saying this layer, that layer, whatever of the OSI, and the layers, when we refer to these things, we say, oh yeah, we're going to use the TCP/IP model, but when they talk about layers, think OSI model, not TCP/IP. Easier to develop, reduce complexity, allows easier program changes and faster product development. Again, specialization, multi-vendor interoperability, modular engineering. I told you I got some of these duplicated. This is kind of a summary of what goes on at each layer of the OSI model. Layer 1, physical, just like in the video, physical, data link, network, transport, session, presentation, application. The one on the left gives an idea of what it does and what runs there. I've had a number of people, or a guy that I communicate with at another institution says that know the OSI model when you, I don't know how many questions you'll be, but it's kind of like what happens there. Down here at the bottom, the physical layer, media, signal, binary transmissions, and then the things that are running there. Physical addressing, Ethernet, and some of those things, the frame relay that we talked about a little bit earlier. I don't see PPP on here. Yeah, I do. PPP, point-to-point protocol. The network layer, path determination, logical addressing, IP addresses are going to be there. End-to-end connections at the TCP, the transport layer, and we're going to look at each of these layers individually here for a few minutes. And then the mnemonics that you may want to use. All people seem to need data processing, or from the bottom up, please do not throw sausage pizza away. So remember those things. And then the top 3 layers here, applications on end devices. The bottom 4 layers are for data shipping, to actually get it from one location and all the information. This one, Carl, this and these presentations, and I think that, yeah, in the OSI model, I think I've got this one in there. If I don't, I will. Yeah, in the OSI model folder in the share, you'll have it there. It's this photos there if that's what you're looking for. But it's in the share in the OSI model. There is an OSI model folder which has some other information available in it. But those things available. So the physical layer. The physical layer, at the physical layer, we don't show the media. The media is really not, believe it or not part of the physical layer. It's the media. The physical layer defines the electrical and physical specifications. The physical specification, we're going to use RJ45. We're going to use coax. We're going to use fiber. But the media itself isn't there. The electrical, how much voltage are we going to use? What are we going to use to encode the signal on the media? So those are the things that are going to happen at the physical layer. Defines the relationship between the device and a physical transmission media. For example, electrical cable, fiber cable. Includes the layout of pins, voltages, line impedance, cable specification, timing, symbol characteristics for connected devices, and the frequency 5 gig or 2.4 gig for the wireless devices themselves. Responsible for the transmission and reception of unstructured raw data in a physical medium. So what we have here are bits. We have ones and zeros. Now they're encoded, not necessarily grouped together so that we can increase the speed of these things, but we have raw data, ones and zeros on this thing. The bit rate control is done at this layer. The bit rate are the number of changes per second. We're going to have a bit rate actually is a data rate. I take that back. Bit rates here. We have baud rate, which is the number of changes per second, the number of ones and zeros that change per second, and bit rate, the number of bits, the amount of data that goes across these things. Define the transmission mode. Simplex. Simplex is one way. Like a radio station would be a simplex. A half duplex or a full duplex. And a half duplex means that's what a bus is a half duplex. We can transmit and we can receive, but we can only do one at a time. Half duplex. Full duplex, we can transmit and receive and do both of them at the same time, which is really kind of cool. And that's one other thing with the switched Ethernet is full duplex, which means that if we have a 100 megabit connection on it, we can transmit at 100 and we can receive at 100, so we can have effectively at 200. Full duplex, transmit and receive at the same time. Defines a network topology, the bus, mesh, ring being some of the most common. The one that, but we keep saying bus. When we use switched Ethernet, it's switched Ethernet. It's not really the bus anymore. We don't have collisions because we have full duplex. What interstate highways were designed to do to reduce, eliminate, they didn't eliminate, but hopefully reduce to some extent collisions because we have two lanes, separated lanes. So we can go north and south, east and west, transmit and receive and do both at the same time. Physical layer, low-level networking equipment, hubs, cabling, and repeaters operate at this. The physical layer is never concerned with protocols or other high-layer items. Hardware at this layer are the network adapters, repeaters, hubs, modems, and fiber media converters. The topology, physical layer identifies the topology to be used. In the common ones, we're going to have the ring, mesh, bus, star, hybrid. What are we going to use there? The next step up, I've tried to put pictures of some of the things that you might see here, is the data link, node to node data transfer, node to node, point to point, node to node. So it's going to be a point to point, when we do that. We're going to have physical addresses here. So we can go from one to the other. They're called physical addresses or MAC addresses or fixed addresses, or if you're doing Cisco burned in addresses, a lot of different names for these things. Between two directly connected nodes, it detects and possibly corrects errors. Very, very little error correction here. That's going to be done up a little bit further in the stack. Defines the protocol to establish and terminate connection between two physically connected devices. Also the protocol flow control between them. IEEE 802.2, and the 802.2 is the IEEE protocol that defines what goes on here. And Ethernet is what we've talked about, and that's what most networks use. Ethernet is defined at layer 2. And what makes an Ethernet an Ethernet? It uses CSMA-CD, carrier sense multiple access collision detection. What does that mean? If we have a true bus, a true Ethernet, we have multiple access, we have all of these things connected together. Carrier sense, there is a carrier signal that has to be modulated in order to do that. Carrier sense, multiple access, and then we talked about we could have collisions on this thing. Does collision detection, does the random back off and starts the process all over again. If there is one, divides it into sublayers. The media access layer, the MAC layer, for controlling how devices in the network gain access to the medium. We could have token ring. We could have the token. We could have token bus. We could have Ethernet. We could have switched Ethernet or switched Ethernet, which we don't really have the shared media there. We have a kind of a dedicated media. Logical link control for identifying and encapsulating network layer protocols and controls the area. And that sounds like something really complex. And when we look at one of these things, it's going to say that what the next protocol is, like IPv4. So I call it a protocol router. It determines what the next protocol is. So when it gets to the next layer up, which is going to be the network layer, there's no surprise about which protocol it's intended for. The MAC and LLC 802.1 networks, 802.3 is going to be wireless, or 802.3 is going to be Ethernet, 802.11 is going to be wireless. 802.15.4 is Zigbee, and that's why I put this thing over here, Zigbee control. This one is for it says sensors. A number of sensors are going to be controlled by this thing, so it's going to be part of the Internet of Things that we use. Point-to-point protocol is a data link layer, PPP. Some of the other ones we would have here, PPP, and in Cisco we would have this one called HDLC, high level data link control, frame relay. Oh, we had DSL, I think, for those. So again, a lot of these, and they are just going to be letters that you're going to need to know, basically what they stand for, where they work. But these things, these protocols, these languages, these technologies work at the OSI model. So we have physical layer, which had the voltages and how we connect to it, and we had bits, raw data on it. The data link layer, how we get access to the medium, because the next layer down, physical layer, is the media layer. How we get access to it. We can connect from one device to the other. We're going to use that magical MAC address. That's the one that it actually gets delivered to. So we have physical data link layer. The next layer up, more layer 2 protocols. The next layer up is going to be the network layer. But the protocols and technologies, HDLC, some of the ones that I wrote there. The token ring, layer 2 tunneling protocol, point-to-point protocol, point-to-point tunneling protocol, spanning tree, which we get to talk about a little bit later, and VLANs, virtual local area networks, which we'll talk about a little bit later also. But these are all things that operate at the layer 2. The devices at layer 2, switches. Hubs run at layer 1. They're a bus. Switch operate at layer 2 because they use the MAC address, and we'll use really big MAC addresses. They're 48-bit addresses, but we're going to use 1 bit. So if I have A here on port 1, and B here on port 2, and C here on port 3, when the MAC address table is constructed, and we'll look at how it's constructed when we talk about switches, we have the ports listed 1, 2, 3, and the MAC addresses that are on it, A, B, C. When A wants to go to B, it gets into the switch, and the switch looks at the MAC address, the destination MAC address, and says, hey, you're going to B. I know where that is. So it sends it directly to port 2. C over here never sees that traffic. So we can make it, the switches make it a little bit better. Switch uses the MAC address table. And we also create virtual VLANs, virtual local area networks on switches. But the next layer up, responsible for addressing, these are temporary addresses or logical addresses. IP addresses can change. IP addresses do change. Physical addresses. So it's responsible for routing the packets from a source to a destination through the network and ensuring data delivery. We use another protocol called ARP to determine which MAC address, which IP address, the MAC address, the IP to MAC address relationship, and then we use the MAC address to do the final delivery of the data. Controlling congestion on the network, taking proper routing decisions. So routers are going to be the devices that operate at layer 3, the network layer, to do these things. Protocols for connecting 2 or more networks, and the logical addresses, IP is going to be the protocol that we're going to see predominantly used here. Packet forwarding, path determination, chooses the best route. Routers use routing protocols, the protocols that they use to communicate with each other to figure out what's the best way to get there if we're using. So routers, IP addresses, routers operate at the network layer. And the one on the right says layer 3 switches. I want to get into them, but yes, they do. Layer 3 switches also operate at layer 3, which is kind of also you'll hear them called multi-layer switches. They can be both a layer 2 or a layer 3 switch. Kind of a neat thing. Some protocols that are going to be at layer 3, RIP, I said IP. IP is the addressing protocol. Protocols that are used to do other things, RIP, OSPF, EIGRP, and IS-IS, are the protocols, the routing protocols, the protocols that routers use to communicate with each other to share information so that they can create routes to find the best path from one to the other. IP is the addressing, the predominant addressing protocol, or it really still is the predominant protocol that's going to be here. ARP, Address Resolution Protocol, what the Address Resolution Protocol, ARP, does is relates the IP address to the MAC address. And the MAC address is for final delivery. The IP address finds networks. It finds the building. It finds the room. The MAC address finds the seat that it's in. ATM, IPsec, Asynchronous Transfer Mode, ICMP, multi-protocol label system, some of the other terms that we have. The next layer up, and this one becomes a little bit busier because this is where our reliability comes in. I think I want to look at some of this while we are here, if I can get Wireshark going. And again, there are scans in that shared folder if you want to get Wireshark and look at them yourself. The things are in here, and I can make it a little bit bigger. We talk about this ARP protocol. Who has 192.168.100.1? Tell 192.168. Looking for a MAC address when we do those things. So who has, and then the 100.1, they're all looking for, this is the who has 100.1, tell 100.165. They're looking for the MAC address of the default gateway in order to get to the internet or whatever. When we start up with TCP, we have this thing, and I'm trying to get to it, called a three-way handshake. And part of, I think the little video said, hey, what we do is we guarantee delivery. We guarantee delivery. You guys that are in the military don't remember back when you actually probably had to write letters. And being on a ship, you never knew when the mail was going to go out. And being deployed, you never knew when it was going to get there, or how it was going to be routed. So we would number the letters. And you would send them, 1, 2, 3, 4, 5, 6, 7, 8, 9 on down the line. They may get home as, 4, 7, 3, 2, 1. What that allowed was, 1, to be sure to know that you got all of the letters, and 2, that you could put it back into proper order. So that, say, this doesn't make any sense. Well, you didn't get, you just read letter 7 and you didn't get 5 yet. So that's what this TCP does for us. And what this SYN does, it's called a SYN, a SYNAC, and an ACK. A SYN is a synchronization packet. And this has got a couple of them here. The synchronization says, hey, I want to have a conversation. And I want it to be a reliable, is what it's called a lot of times. I prefer connection oriented, but reliable, because we're going to guarantee, we're going to number all of the data that goes out to be sure it got there. If it got there and out of sequence, we can put it back into sequence. But when we start it up, we've got to establish a numbering system, and that's what this does. The SYN packet, it says sequence, big number here, 667 is what I want you to remember, because when we go down here with the ACK, the acknowledgement 668. It just increments it by 1. We have some other stuff in here, window size. Instead of sending it one piece of data at a time and acknowledging it, we create a window. We send a whole bunch of data, and then we only have it to acknowledge that amount of data. The transport layer is where a lot of the is it working takes place. So we have the synchronization, and we have a big number that says, hey, here's the starting number system that I'm going to use. The other end says, okay, I acknowledge yours, and that's what the ACK was, incremented by 1, because there's no real data here. And I want to have my own numbering system. And if we go over here, this one's 663 to 664. When we actually start sending data, the only thing we're going to get is acknowledgments. And we get the sequence number, and acknowledgement. And we have the window size and all those other things that go on. But once it gets going, the only thing that you should see is acknowledgments. And it acknowledges based on the amount of data that it has. But the TCP IP three-way handshake, the SYN ACK SYN actually, and then the ACK, to establish a connection between two different locations. And the reason I want to say two different locations is because when we get up a little bit farther, he's going to say, hey, we control communication. The session layer creates sessions between applications and controls how much data flows. So this would be like maybe calling into a building, and then the session layer is going to be which extension that you get within the building. But we have the three-way handshake, and then we have acknowledgement of the data as it gets sent. And when we talk about these things, we have the Ethernet, we have the destination, we have this is what a MAC address looks like, 94.10, 3E, 6E, 4888. It's a hexadecimal address. The destination address, the source address, this is the protocol, the LLC, the next protocol up, IPv4. And then the next protocol down here, IPv4. The source address, the destination address, and some other flags that go along with it. Protocol, TCP. So it's using TCP. The next one up is going to be the TCP protocol. The transmission control protocol. The source port and destination ports, we'll talk about those a little later. The sequence and the acknowledgement numbers that goes on with these things to put them together. So it's got a little bit more information in it. It goes on and on and on. So this one says it's an acknowledgement. It's the flag that's set on it. So again, I like to look at these things. There are scans. If you want to look at scans, you'll have to download Wireshark in order to do it. But it's free and safe. You may want to do a scan look at your own network to see the amount of traffic. And it's just, it's phenomenal the amount of traffic it's on even a small network. So the transport layer accepts data from the upper layers, this is when it's coming down, and breaks it into smaller units known as segments. So transport segments. And we'll go through, I got another one for they're called PDUs, protocol data units. And we'll go down these things, and up here we'll have data. And this will be don't. And then the transport layer, here we have segments. So the transport is segments. The network layer is people, packets, frames, and then bits. The mnemonic is don't, some, people, fight back. And these are called protocol data units. The data units, segments, packets, frames, and bits. They go on here, and the D up here just say data, just to have something to start it with. So it has segments to the lower layers and ensures that all segments arrive correctly at the receiving end, because we have the numbering system. We had the SYN and the ACK, and then the SYN and all that other stuff, and then we number it as it goes out. Adds a sequence number to each segment. Helps reconstruct the original sequence and to be sure the outer order sequences, and to be sure that we got everything. That's where the reliability comes in, is when we do the numbering. For error detection and sending acknowledgments at the network level. So the ACKs, yeah, I got it all. And what this is showing is this is one packet. We send packet 1. So we receive packet 1, ACK 0. So we acknowledge receipt of that. We send packet 2. So receive packet 1, send an ACK of 1. Then it sends packet 2. We don't get it. We don't acknowledge it. So it sends packet 3. It says discard, send ACK 1. We acknowledge receipt of packet 1. We didn't get 2 yet. On down the line till here it finally says, okay, I got packet 2. Now we can go on with it. But we have acknowledgments that I have another little demo. We're going to have not a whole lot of lab time tonight. No, I don't. We'll look at it. It's the moving window. I think we'll talk about it a little bit later anyway. Transport data between devices. The protocols are TCP and UDP. I spent a lot of time with TCP because of the reliability. UDP is sometimes called an unreliable protocol. It doesn't have any of that start up to the three-way handshake, the establish the connection. It just sends the data. And something else has to actually to check to be sure it got there. If you ran a Wireshark on this meeting that's going on right now, it's using UDP. Streaming uses UDP because you couldn't possibly acknowledge all of the small data packets that are coming into protocols at the transport layer. Ensure that the data is correctly sent or received. Service addressing, the number of protocols support many network services, ensures that data is passed to the right service at the upper layers of the OSI model. Segmentation to traverse the network blocks of data broken into packets of manageable size. For the lower layers, we have the segments and then the network packets. And then below that, the data link frames, and below that we had the bits. Buffering and windowing. Buffering, the flow control is used. The data is temporarily stored. If we are going too fast from one to the other, then we can, you see I'm trying to do something else, try to do this sliding window thing because windowing is here. If the other guy says, hey, you're going too fast, slow down, we can buffer and keep the information. When it gets to the other end, it goes into a buffer. When that buffer gets full, that's when you go back to the other side and say, hey, slow down. So buffering can cause a problem if the sending device is just transmitting the data too much. We saw a window size in there. This is kind of a little demo of the moving window. What happens? We're going to send data from one to the other. We can adjust the size of the window. Right now it's 4. We can make it big or little. And let's just do the 1 here. Let's do a 0 loss when we do this thing. We can start it. The data goes ABCD, goes up here. And now we're going to come back down and we acknowledge ABCD. And the window moves across to EFG. So as we get the acknowledgement, the sender window moves along as long as we keep getting the acknowledgements from the receiver. I'm going to let this finish and then we'll introduce some losses in there. All the data doesn't get acknowledged. It didn't get there for whatever reason. Or it got damaged. So we got there. Transfer is complete. We can do a restart. Well, let's do a 20% loss. So we're doing good so far. A, B, C, D, and up. We didn't get all the acknowledgement. You notice that it only moved over. Actually, it did get the acknowledgement. It moves over a little bit, this thing really, but this one didn't get there. So we're sending G again. The thing about these little simulators is sometimes they have their own mind. But the sliding window as the data is received or as the acknowledgements are received, it gets sent across, and then as the acknowledgement happens, the window moves and we send more than one data packet at a time. Make the system move a little bit bigger. So windowing, data is sent in groups of segments. Only require one acknowledgement when we get there. The size of the window, how many segments, is defined when the session between the two devices is established. When we do the startup, we establish that. Transport layer, quite a bit going on there. The session layer controls dialogues, connections between computers, and I should say that's hidden there behind these little guys that are talking, controlling the dialogue here. Between computers, establishes, manages, and terminates connections between local and remote application. And here the key is applications. TCP does its connection between locations. Session between applications. Provides for full duplex, half duplex, or simplex operation. checkpointing, adjournment, termination, restart procedures, graceful close of sessions, control multiple bidirectional messages, allows the presentation layer seamless view of the incoming stream. Each of the layers of the OSI model supports the layer. So the session layer is trying to make everything easy for the presentation layer. Presentation layer to present it to the application layer when we do those things. And then some protocols there, NetBIOS, network file system, and server message block, which are SMB is Microsoft's file sharing protocol. Session layer primarily responsible for setting up and managing communicative sessions, thereby enabling the sending and receiving data an undetermined length of time. So it's going to control who gets access to what. Presentation layer, encoding the data, standard network compatible format, to be sure that each end can communicate with each other and that the application layer is going to understand it. Data formats are standard data formats. Translation is only an intermediate format and will change at the lower levels. Encryption is a service that happens here. I guess I'm running everybody off. Presentation layer, the graphics, text and data, sound and video are going to happen at this layer. So the things that are going to happen at the presentation layer, can we actually read the data? Application layer, closest to the user. This is where the services and the applications are. Does not provide services to other OSI layers. This is the one that we're going to connect to. These are where the services run that allow us to get the information from point A to point B. So only to applications outside. It only connects to applications outside of the OSI model. Synchronizes and establishes agreement on procedures for error recovery and control of data. These next slides are a number of ones that have different, definitions, explanations, text about the different layers. Application layer, presentation layer type of data, and these are what goes on, starts and ends sessions, and also keeps them isolated, defines ports and reliability. We'll talk about ports later, but we did talk about reliability. Network logical IP addressing, data link layer with the switches and the MAC addresses. Physical layer, cable, network interface cards, electrical signals were there. And another one, again, some just different slides, different things. Each of them kind of addresses a different element of the OSI model. The OSI model, or the layers themselves, actually do two different types of communication. They do peer-to-peer. The application layer talks to the application layer, presentation to presentation, session to session, on down the line. They also have adjacent layer communication, so that the physical layer 2-to-1 talks to the data link to network, and on up the line. So peer-to-peer as well as adjacent layer communication. This is another one of those that just has, I guess, a bunch of stuff that is connected to it to do these things. The different elements, just another summary of what goes on, some end-to-end devices, and then some pictures of some of the devices that are going to be. The TCP IP model, originally called the DoD model because it was developed by DARPA, the Defense Advanced Research Project, who did invent the internet. To allow the new technologies, it actually was built to model how the communication took place. But if you look at the one over here, it does the same, except that instead of having these three upper layers, we just call all of this, we lump it all together and call it the application layer. The transport layer, we just simply, still TCP and all the other things that we talked about, we just renamed it host to host. The network layer is still IP and ARP and all of those things, and instead of calling it network, we call it the internetwork layer. The same devices are going to be working here. We group the data link layer and the physical layer together and call it the network access layer. Because, and I think one of the slides said that the MAC address is down here, And a lot of times I say the MAC address is a layer 2. So where is the MAC address? If we put them all in here, the MAC address goes into these things. So it does the same thing, a little bit different terminology, but it actually models the way the TCP/IP protocol works. The link layer on this one, the network access layer, equivalent to both the physical and the data link layers of the OSI model. Cables, connectors, network cards, OSI layer 1. Like layer 2 of the OSI model, the link layer of the TCP/IP model is concerned with hardware addresses. So the things that happened at layer 1 and layer 2 of the OSI model are at the bottom layer, the network access layer, TCP/IP. The internet layer directly aligns with layer 3 of the OSI model. Network layer IP addresses, routers, routes data, IP addressing, routes packets to remote host. Fragmentation and reassembly happens here, is where IP operates. So network, internetwork, probably a little bit better name because it actually does go inter-network from one host-to-host. Transport layer does exactly the same thing as layer 4 of the OSI model. Core of the TCP/IP architecture, TCP and UDP operate here. Port numbers, again, we'll talk, port numbers represent services, like HTTP is 80 so that we know where we're going with these things, these well-knowns. We will address them a little later. Application layer 5, 6, and 7 are here to do these things. And the insert at the bottom, the protocols that operate at these different layers of the 4-layer model, the TCP/IP model, allow programs to access the network. I'm presuming it. My mic, I wasn't seeing anything. It wasn't working. So OSI communicates, and there's again a number of different elements that you can maybe go review if you want to when we look at these things. Layer 7 communicates with layer 7, peer communication as well as adjacent layer communication happens with these things. We encapsulate it as it goes down. We have the data, the TCP, as you saw hopefully in the Wireshark. The header information goes on top of the data. The TCP header, the IP header, and then the LLC header, the data, and the MAC header, the things from the data link layer that encapsulate one from the other. And then the PDUs are over here, segment, transport segment, and again, don't some people fight back for the mnemonic for that one. Segment, packet, frame, bits for the protocol data units for each of, more just summaries, and I guess I kind of went overboard, but each of these I think shows a little bit different element of the models, the OSI and the TCP/IP models. This one again, protocols, the TCP/IP model, the protocols that operate and get different protocols within these things. The network access layer down here, the PPP, Ethernet, interface drivers all operate at this layer. And it shows ARP is kind of between the two. ARP is the one, address resolution protocol, that relates the MAC IP addresses together. A little bit of summary of what goes on at each layer of the OSI. And then there are a few questions here, and then there's a short little session after this. We'll take a break and then do it and then finish up. Order the layers from the bottom up. And as we can use the please do not throw sausage pizza away here, right? Anybody? Thank you, Celeste. Yes. Physical, data link, network, transport, session, presentation, application. Match each protocol with its layer. So Ethernet is which layer? Ethernet, I got a network. Anybody else? Got 4. Network. Ethernet. Well then, where is IP? If Ethernet is at the network layer, where's IP? At the internet. Oh yeah, we don't have network on here, do we? IP is the network. Ethernet is at about the network interface. And this is the TCP, which you probably won't get. HTTP, application. TCP is still going to be at the transport. And then IP is going to be at the internet. And see, I'm still thinking OSI. I read TCP and I'm thinking OSI. Which models assume two protocols on one layer will not communicate? Choose the best answer. The OSI. What transport layer protocols carry network data? TCP, UDP, both or neither? We'll go with both on that one. And this is the troubleshooting process. You guys want to take a quick break? Maybe come back at, this one is actually pretty short. Let's come back at 20 past and we can do that. Did I really run everybody else off? I guess. So go ahead and take a break and let's come back at 20 past. Questions or comments? Do the model share protocols or no? They share protocols. It's just the way that they had them. Yeah, and that's fine. I don't have any problem with that at all. Take a look at the troubleshooting process. What CompTIA likes to do on their test for the troubleshooting questions is, you've done this. What's the next step? So the process, the steps, what happens at each level of the troubleshooting process, kind of a big deal to know. And the one on the right is exactly the topics here about the importance and then how to troubleshoot network problems, the CompTIA way. Those of you who are in the military and the Navy way, the right way, the wrong way, and the Navy way. So we got the CompTIA way is the process, and it is the right way. But define the problem, hypothesize the probable cause, test the hypothesis. If it doesn't work, do another one. If it does, test the hypothesis. Plan of action, implement the plan of action, verify that the problem resolution, and then create a post-mortem report. Those things. That's from another one I've got. We're going to have the actual CompTIA one, identification, learning that there is a problem. It may be a while before you find that out. Is there a problem? And maintaining, reading logs, maintaining plots of what's going on is a big deal, because a lot of the problems, network problems, occur over time. They occur gradually, so that it's not anything that just happened. Diagnosis, the extent and the root cause, and then the resolution, planning to fix the problem. This is another, what goes on. What do we do at each of these things? Define the problem. Listen, ask questions, examine. Asking questions, and you have to be careful of the way that you ask. What'd you do? And I tell you what the answer is going to be. I didn't do anything. I just turned the computer on and it didn't work. But ask questions, listen, what happened? When did it happen? Can you replicate the big issues here? Isolate, observe, narrow your search, zero in on the cause. Make a plan. Repair or replace. Follow the plan, and then conduct the repair. After that, ensure that everything works. We're going to test the solution, and then we're going to document the repair. So, I mean, and all of these came from different places, but the process is going to be the same. The troubleshooting model, the CompTIA on the left, identify the problem, establish a theory or probable cause, test the theory, establish a plan of action, implement the solution or escalate as necessary if we can't resolve it, verify full system functionality, and if applicable, implement preventive measures, and then document the findings, actions, and outcomes. Identify, gather information, symptoms, question the users. Can you duplicate the problem? And if we can replicate the problem, that's kind of a big deal, because the random ones are the ones that really do drive you crazy. Determine if anything has changed. That's me. I don't document well, but I change things. And my wife will be using the computer and say, this doesn't work. What'd you do? I didn't do anything. And then, 2 hours later, it dawns on me, oh yeah, about 2.5 weeks ago I did this, and that could be affecting that. So what has changed? Has anything changed? And that's where documentation of changes that you make really come into play there. Approach multiple problems individually. Don't group them together. And when you're doing things, do one thing at a time. If you do 3 or 4 and it fixes the problem, you don't know what fixed the problem. And you could introduce other problems when you do that. So one thing at a time, one problem at a time, systematically. Troubleshooting the approaches, top-down, and this is the OSI model, top-down or bottom-up, or divide and conquer, start in the middle, follow a path. How are you going to do it? And the reason the model comes in, what's not working? What layer isn't working? What part of the OSI model isn't working? Can I not get to the network? Is it the network addressing? So is it a router issue? The route table is going to be a problem. You know, you work your way back from those things using what we're going to do with the OSI model. You're going to start at the top down, the bottom up, divide and conquer, start in the middle of the stack. And after you've done it for a little while, and not really that long of a while, you'll have an idea of where you need to start. But you got to start somewhere. Track the traffic through the network. What happens to it at each location? I used to say, be the packet as it comes in. What happens to it? What is happening to it? What should happen to it? What is the issue with these things? Spot the differences. Move the problem. Move suspect components, and they keep track of what you did, what fixes it. Test your theory. Sanity check. Is there any reason the theory couldn't explain the problem? Verify, and here is the escalate if necessary. This is if my theory is not going to work, it absolutely could not. An action plan. Quantify what changes we need to make and identify what we'll need to execute. Create the plan. Consider the side effects of the plan. Create a backout plan. We had some folks that worked at Advanced Auto, and when they wanted to make changes, they did it all with scripting. But before they could run their scripts, they had to have a script that would undo any changes that they made. So have a backup plan. If it doesn't work, we need to be able to get out of this thing. So backup plans. Implement the solution. Suitable time. That you have all you need on hand. You've got all the parts, the components that you need. Be prepared to escalate or roll back with these things, and let people know what's going on. Schedule suitable time and notify everybody. After you get done, document the outcome. The issue is initially reported, underlying cause. What'd you do to fix it? Complications, errors, any other particulars that are specified by your organization. So, and different organizations may have different requirements. This is the steps from the top down. Identify, establish a theory, test the theory, establish a plan of action, implement the solution, verify the function, and then document the findings. And I told you this was a quick one. So the assessment, and I'm just going to do these things, and we just did this. So it's identify, establish a theory, test the theory, establish a plan of action, implement the solution, verify the system function, document the findings. The user problem reports can't be entirely trusted. True or false? I'm going to have you guys. Can you absolutely trust these guys? No, you can't. True, you can't trust them. And it's not because they're not trustworthy. They maybe not know what they're looking at, maybe not know what they're reporting. And it's all of those that, do they really know what they're looking at here? The user reports being able to access websites but not send and receive email. What troubleshooting approach would probably be the quickest? Bottom up, top down, divide and conquer? Anybody? Bottom up, bottom up. Oh, bottom up. How about top down? Because what we're talking about getting to the websites, but he can get to the websites, but can't receive an email. Some application's not working somewhere. So we can't get the email. The odds are it's going to be the email server, which would do those things. Instead of, although the bottom down, it could be communication down here. So it is just a matter of how you want to approach it. I usually start right in the middle because actually I start at the bottom because most of our problems actually were media problems with wires that somebody had not made properly. The user who first reported a problem is often the best person to verify that it's been fixed, true or false. The one that knew what wasn't working right. I fixed it. Are we going to let them test it for us? I got a false. Anybody else? False, false, and a true. We'll go with a true on that one. They're the ones that have been working with the machine. They're the ones that had the issue, so they probably are the best ones to say, oh yeah, it's working now when we do those things. But back to them, it always gets into a lot of, you can't trust them for the reporting, but yeah, we'll trust them to. So the summary, we talked about terminology, connectivity, components of the network, challenges, general challenges, the availability, reliability, and all of those things. Networks are classified, the scope, the topologies. We talked about topologies, resource sharing models with the peer-to-peer and the client-server models. We looked at the OSI and the TCP IP models, similarities and differences, uses and technicians and engineers, and it's just a matter of how distinctly, I guess, you want to break those elements down. The TCP IP model to me makes a lot more sense because particularly down to, I mean, at the upper layers, in the things that we generally worry about, getting data from one to the other, not a whole lot happens at the upper layers. At the lower layers, a lot of things happen, but at the lower layer, the network access, instead of the individual physical and data link, combine those two because it's where the NIC plugs in, it's where the media plugs in, it's where the MAC address is. All of those things happen. And then how to approach the troubleshooting process. And again, when CompTIA does this, it's you've just done this, what's your next step sort of arrangement. So there is a little bit of time left. What I have here in the share, there is a folder that says lab sequence, and it's little text documents, which instead of trying to figure these out from the syllabus, these are the labs from the test out, the numbers from the test out website. And tonight is like the 0.2, the first two. And if you've done these before, it's the how to use the site sort of arrangement. But again, there is a lot of good information there. Questions or comments? I'll be here until the time's up. But if you have questions or comments, let me know. Either you can do it in the chat or just unmute, talk, going once, going twice. Let me see if I can show you what you hopefully will see with that, with the labs over here, and over on the right is where studying, taking, accessing your lab and test prep environment, test out. So when you click on it, the lab sim, and you got to log in, and they should have provided you a username and password. Sometimes I get one, sometimes I don't, but the lab sim test out is where those things are. Are you ready to call it a night? Have a good evening. It's time to call it a night. Hope everybody is ready. If you're working on labs, feel free to keep going. I know for all you guys on the East Coast, it's getting pretty late. Have a good evening. See you tomorrow.